Imagine for a moment, right? You're trying to prove something absolutely critical, maybe a financial audit across multiple banks, and these banks, they don't trust each other. Or maybe you're combining super sensitive health data from different hospitals for, vital research. The catch is the crucial info is split up, held by all these different parties who are frankly suspicious of each other. So how do you prove a collective truth without anyone having to spill their individual secrets? Welcome to the deep dive. Today we're jumping into something called collaborative zk-SNARKs. Sounds complex, I know, but our mission here is to really unpack how this pretty groundbreaking cryptographic idea is making secure private collaboration possible on a whole new scale. We're going to look at how multiple different groups can work together to generate a single zero-knowledge proof. A proof about their combined private data, but crucially, without revealing any of that data. Think of this deep dive as, well, your shortcut to understanding some really cutting-edge privacy tech. We'll be looking mainly at two key papers that really push this field forward. The first is Experimenting with Collaborative zk-SNARKs by Alex Ozdemir and Dan Bone. That one sort of laid the groundwork. And then there's Scalable Collaborative zk-SNARK and its application to fully distributed proof delegation, which really focused on making these things practical, scalable for the real world. So be ready. We're about to explore some seriously clever solutions that are kind of redefining secure teamwork. Okay, so let's start with the basics, maybe a quick refresher. For anyone new to this, or maybe just needing a reminder, what exactly is a ski-snark?
Right, okay. So a standard zk-SNARK that stands for zero knowledge, succinct non-interactive argument of knowledge. It's basically a way for one party, the prover, to convince another party, the verifier, that a statement is true. But here's the magic. They do it without revealing why it's true. That's the zero knowledge bit. Plus the proof itself is really small. That's the succinct part. And the verifier can check it super quickly without back and forth, which is non-interactive. The prover has a secret called the witness, which is their private input, and they use that to make the proof.
Okay, so one prover, one secret piece of information, and one proof. Simple enough in theory, but like you said, the real world, it's messy. What happens when that secret, that witness, isn't just held by one person? What if it's, spread out?
Exactly. And that's precisely the gap that collaborative zk-SNARKs fill. They aren't really a totally new thing, but more like an extension. They adapt traditional zk-SNARKs for a multi-party world. So this allows multiple parties to work together to jointly generate one single proof about a statement that depends on all their private data. And the key is, they do this without any single party having to show their private piece to anyone else. Each person just holds their own share of the overall witness. The analogy I like is, imagine a bunch of detectives. Each one has found just one piece of a really complicated puzzle map. They could work together to prove to the chief, hey, the final map looks like this, and the chief can verify it's correct. But crucially, none of the detectives ever had to show their individual piece to any of the other detectives.
And that's fascinating because the core properties, zero knowledge, the proof being small, easy to check, those all stay the same, right?
Yeah.
The verifier on the other end doesn't even need to know multiple people were involved. The change is all hidden inside the proof generation step. It becomes this distributed effort.
Precisely. The interface for the verifier is identical. All the complexity is managed collaboratively by the provers.
So, okay, it's cryptographically neat, but why is this such a big deal practically? Where do these collaborative systems really shine? What kinds of problems do they unlock?
Well, the applications are pretty wide-ranging. It really comes down to situations where you need both decentralized data integrity and privacy. Think about verifiable aggregate statistics. Say, in healthcare, different hospitals might want to collaborate on research. They need to calculate, maybe, the overall effectiveness of a new treatment across all their patients combined. With this, they can prove the final statistic is correct, based on all patient data, but without any hospital revealing its specific patient records to the others or to the researcher. That's huge for privacy. Or take decentralized audits. Imagine a group of banks, or maybe nodes in a blockchain network. They might need to prove something about the whole system, like total assets across all participants equal total liabilities. Ooh. They can generate a single proof of that global property without any single bank revealing its sensitive transaction details or balances to the rest of the network. Then there's proof delegation. This is interesting. A user with, say, a smartphone, not much computing power, needs to generate a complex proof. They can split their secret witness data and send shares to multiple powerful servers. Those servers then collaborate to compute the proof for the client without ever learning the client's actual secret data. And one more. Publicly auditable MPC. Multi-party computation lets groups compute on secret data, but the results are often hard to verify publicly. Collaborative SNARKs allow the MPC to produce a small, easily checkable proof that the computation was done correctly.
Wow, okay. So you can get these combined insights, run audits across untrusting parties, even delegate heavy computation, all while keeping the underlying data completely private. That feels incredibly powerful. But I imagine making this actually work wasn't trivial. What were the really big technical roadblocks they had to overcome?
You're spot on. It's definitely not straightforward. The early work, like that first Azimir and Bonnet paper, really highlighted, I'd say, four main challenges. First, just distributing the computation securely. How do you get multiple parties who might not trust each other to coordinate on a complex calculation like SNARK proving? You can't just run the standard prover algorithm inside a generic MPC framework, multi-party computation. It's just way, way too slow. You need specialized protocols. Plus, you have to handle things like, what if one party just drops out or acts maliciously?
Yeah, the trust issue.
Exactly. Which leads to the second challenge, maintaining privacy between these mutually distrustful provers. Even if they're collaborating, you have to assume some might try to cheat or learn other secrets. The system has to guarantee that individual secret shares stay confidential, even if some subset of the provers decide to collude.
Makes sense. Security and privacy, always linked. What else?
Third, efficiency and scalability. As I mentioned, MPC can be slow. zk-SNARK proving is also computationally heavy, putting them together efficiently. That's tough, especially if you're talking about large data sets, complex calculations, or many, many participants. You need it to scale reasonably well.
And the last one.
The fourth one is sort of a compatibility requirement, creating proofs identical to single prover versions. The final proof that comes out of this collaborative process must look exactly like a proof generated by a single prover using the original zk-SNARK scheme. This is crucial so the verifier doesn't need any special logic. They just run the standard verification check they always would. It keeps things simple and compatible.
Okay, so it's a balancing act. Secure coordination, prover privacy, decent performance, and it has to look like a regular proof at the end. That's quite a list. So let's maybe zoom in a bit. What really sets these collaborative systems apart from the standard single prover ones? What stays the same and what fundamentally changes?
Well, the good news is the core guarantees that make zk-SNARKs powerful are preserved. You still have completeness. Honest provers working together will successfully create a valid proof if the statement is true. You still have soundness. Nobody, not even a group of malicious provers, can trick the verifier into accepting a proof for a false statement. And you still get succinctness. The proofs remain small and verification stays fast. Like we said, the verifier's job doesn't change. All the new complexities on the prover side.
Okay, foundation is solid. But where do the really interesting differences, the new cryptographic properties, come in?
Right, the subtleties are key here. First, the notion of knowledge soundness shifts slightly. In a standard SNARK, if a prover gives you a valid proof, it implies they know the secret witness. A theoretical extractor could pull it out. In the collaborative setting, a valid proof implies the group collectively knows the distributed witness. The extractor recovers the combined witness from the group effort, not necessarily that each individual prover knew their piece in isolation, which makes sense. It certifies collective knowledge.
Okay, collective knowledge. What else?
Then you get this really important property called T0 knowledge, or TZZK. This gives a formal guarantee about privacy against collusion. It basically says that even if an adversary corrupts and colludes with up to the provers, they learn absolutely nothing about the private data held by the honest provers. Nothing beyond a single bit of information. Was the overall statement true or false? This explicit guarantee against a certain level of collusion, intent parties, is critical for building trust in real-world decentralized systems where you can't assume everyone is honest.
So T-provers can team up, and they still can't learn the secrets of the others. That sounds robust. And the last difference.
The last big one is prover interaction. The prove step, which used to be a single algorithm run by one party, now becomes a secure multi-party computation protocol, or MPC protocol. The provers actively communicate back and forth according to this protocol to jointly compute the pieces of the proof, ensuring that during this communication they don't leak their private inputs to each other. This explicit use of secure MPC is what really distinguishes these collaborative systems from some simpler multi-prover ideas where you might just assume provers are honest and don't collude. Here, you get security even if some are malicious, up to that limit.
Got it. So the verifier sees the same old proof, but under the hood, there's this complex, secure MPC dance creating it. It really sounds like you'd need totally new cryptography. But you mentioned earlier there was a more elegant way, something about adapting existing systems. How did they avoid reinventing everything from scratch?
Yeah, that's one of the most elegant insights, I think. We don't necessarily need brand new SNARKs. We can adapt the ones we already have. This idea is formalized in something called a lifting theorem. The beauty of this isn't just code reuse. It's recognizing that the whole secure, multi-party aspect can be handled by the well-studied field of MPC. So basically, the theorem says, if you have a standard zk-SNARK scheme defined by its setup, prove, and verify algorithms, and you also have an MPC protocol, let's call it A, and this MPC protocol is capable of securely running the original prove algorithm. Specifically, it needs to be secure with abort against in-check corrupted parties. Then, you can essentially just plug the MPC protocol A in place of the original prove step. The resulting system, setup, A, verify, automatically becomes a collaborative zk-SNARK, secure against net malicious provers. This is huge because it lets us leverage all the existing work on making SNARKs efficient and all the existing work on making MPC secure without having to solve both problems simultaneously for every single scheme.
That's a really clever way to frame it, like taking a high-performance engine, the SNARK prover, and fitting it into a sophisticated, armored, multi-driver vehicle, the MPC protocol. The core engine stays the same, but the way it's operated changes completely. Okay, so that's the framework. But the devil's in the details, right? What were the big engineering challenges in actually doing that lifting? How do you make those core SNARK operations run efficiently inside an MPC?
Right, that's where the real engineering grit comes in. Because as we said, just naively running the prove algorithm step by step inside a generic MPC protocol is usually way too slow. It doesn't take advantage of the specific structure of SNARKs. The key, explored in both papers, but especially the second one, is to leverage the specific algebraic structure of zk-SNARK primitives to design highly optimized custom MPC protocols for each building block. Let's start with how they handle the witness, the secret data itself. How is it shared? The first paper, Ozdemir and Bona, mostly relied on standard techniques like additive secret sharing or Shamir secret sharing. They used these within existing general-purpose MPC frameworks like GSC or SPDZ. Now, these methods are pretty good for linear operations. If you need to add shared secrets, everyone can just add their shares locally. Many parts of SNARKs, like KZG commitments or parts of some check protocols, are linear, but they become much less efficient for nonlinear operations, things like multiplication checks, product checks, or checking permutations. These often require lots of communication rounds in generic MPC, which became a bottleneck, limiting scalability.
Okay, so good for simple math, but struggled with the more complex bits needed for SNARKs. How did the second paper improve on that?
The second paper, the scalable one, introduced a more tailored approach, Pack Shamir secret sharing, PSS. Instead of sharing just one secret value at a time, PSS lets you bundle a whole vector of, say, co-secrets into a single share. This allows for SIMD-style operations, single instruction, multiple data. You can perform an operation like addition or multiplication by a public constant on an entire vector of shared secrets almost as efficiently as on a single one. This is much better suited to the structure of SNARKs, where you often deal with large vectors of coefficients or evaluations. It drastically speeds up the linear parts and provides a better foundation for tackling the nonlinear ones.
Right, so using a tool that's designed for handling lots of data points at once, like vectors, makes everything run smoother. A more specialized tool for a specialized job. Okay, so that's the sharing. Now, how did they optimize those core computations? Let's start with, say, polynomial commitments like KZG.
Yeah, collaborative KZG is a great example of leveraging linearity. So, quick recap. Standard KZG lets you commit to a polynomial fx to get a short commitment c. Then you can prove an evaluation, say f as e, with a small proof. But the verifier checks all this, c is e, y. The crucial insight for collaboration is that the main KZG operations committing and proving are linear.
Linear meaning addition-friendly.
Exactly. If the polynomial fx is secret shared additively, like fx f1x plus f2x plus 2 prover I only knows fix. Then to compute the collaborative commitment C, each prover I just computes a local commitment CI based on their own shares, FI. Then they simply broadcast these CI values and everyone sums them up. C keys, CI, done. No private data revealed. And collaborative proof generation is similar. Each prover computes their local evaluation share YI, their local share of the quotient polynomial key, and their local proof share. Then they just sum up the relevant shares to get the final Y and the final proof. This works perfectly because of how KZG is built algebraically, combined with the homomorphic property of additive secret sharing. It's incredibly efficient, minimal communication, just broadcasting and summing at the end.
Wow, that's really neat. It feels almost too easy. Like everyone just does their part locally and then they just add it up. It fits the cake recipe analogy perfectly. But you mentioned KZG was one of the easier ones because it's linear. What about those nonlinear bottlenecks like product checks? How did paper 2 tackle that, especially compared to the first paper?
Right, prod check was a much tougher nut to crack and a major focus of the second paper's improvements. Prod check is needed to prove things like this value h is the result of multiplying together a whole sequence of values, often evaluations of a polynomial. It's essential for things like permutation arguments in SNARKs like Planck. The first paper's approach, using generic MPC for this, really struggled. It basically involved the provers collaboratively multiplying pairs of values and pairs of those results and so on. Even using clever MPC techniques, it ended up requiring communication that scaled, roughly, with a number of things being multiplied. And importantly, it didn't distribute the work very well. Everyone was kind of involved in every step. This made it a serious performance bottleneck for bigger circuits.
Okay, so the old way was slow and didn't parallelize well. What was the breakthrough in paper 2?
Paper 2 introduced a completely different structure, the product tree approach. Instead of a sequential chain of multiplications, they thought of it as building a binary tree. Imagine the values you want to multiply are the leaves of the tree. Each node above them is the product of its two children. The root of the tree is the final overall product h. Now, why is this structure better for collaboration? Because you can parallelize building it.
Ah, like a divide and conquer strategy.
Exactly. You can split the leaves, the initial values, among the n provers. Each prover takes their chunk of leaves and computes the subtree above them completely locally and in parallel. So if you have n values total, each of the n provers handles roughly n leaves and builds their local part of the tree. Then you only need a bit of coordination at the end. For instance, a designated leader prover can collect the roots of all these subtrees and compute the final few layers of the tree to get the overall product h. The proof then involves verifying this tree structure was built correctly, again using collaborative polynomial commitments and checks. But the key is that most of the heavy lifting computing all the intermediate products is perfectly parallelized. This massively reduces the work per prover, it scales like 1n, and cuts down communication dramatically. This is where they saw huge speedups, like that potential 30x gain with 128 servers. It makes large product checks feasible.
That makes so much sense. Instead of everyone waiting in line to add their multiplication step, everyone builds their own section of the product tree at the same time, and then there's just a quick assembly at the top. That's a huge architectural shift.
Right.
Okay, so that fixes product checks. What about permutation checks? You mentioned they often rely on product checks. So did the product tree fix those too?
Well, yes and no. Permutation checks, especially in Planck-like systems, are about proving consistency of wires in the circuit, showing that the value at one point is correctly copied to another point according to a known permutation, often written as x. The classic way to prove this does involve reducing it to a product check, often called the grand product argument. But if you just plug the new product tree approach into that classic argument, it's still not ideal for MPC. It still involves computations on the secret witness values in ways that generate a lot of communication overhead. The Ozdemir and Bona paper basically hit this wall.
So even with a faster product check, the standard permutation argument wasn't great for collaboration.
Right. So the second paper proposed a different MPC-friendly permutation check. The core idea here is super clever. Shift the hard work from the private witness values onto public values. Instead of computing a grand product involving the secret witness V, they represent the public permutation as a public matrix M. The original wiring identity, Vx, equal x-NUX, can then be rewritten as an equivalent check involving this public matrix M and the witness vector V. This reformulation often uses techniques from multivariate arithmetization, basically representing things with polynomials and multiple variables.
Okay, so they changed the mathematical formulation of the check. How does that help?
It helps because the new formulation can be verified using more efficient MPC primitives, primarily collaborative sum check. The protocol goes something like this. The verifier sends a random challenge. The provers use this challenge to compute some values related to that public matrix M. Then they run a collaborative sum check protocol to verify a specific linear relationship holds. This sum check itself boils down to checking a few simpler claims. The final step might involve a standard permutation check, but critically, it's performed on public data derived during the protocol, not directly on the large private witness grand product. By avoiding that private grand product, they dodge the main MPC bottleneck. They can use the efficient packed Shamir secret sharing and collaborative sum check, cutting communication by almost a factor of n, the number of provers, compared to the naive approach. It's a much more direct and efficient way to verify permutations collaboratively.
That is really smart. Instead of wrestling with the secrecy of witness data during the check, transform the problem so the hard part involves public data, making the collaborative part much easier. It sounds like a complete redesign. So, okay, we've got packed secret sharing for the data, efficient collaborative KZG for linear parts, the product tree for multiplications, and this public input permutation check. If we put all those pieces together, what's the final workflow look like for generating one of these collaborative proofs?
All right, but taking it all together, the pipeline for a state-of-the-art collaborative zk-SNARKs, like the one from the second paper, looks roughly like this. 1. Setup. Standard procedure, generate the common reference string, CRS, needed for the underlying SNARK. Everyone gets this. 2. Witness sharing. The secret input data is distributed among the N provers using Pack-Shamir secret sharing, PSS. Each prover holds shares of vectors of witness values. 3. Core algebraic operations. They run the optimized MPC protocols. Linear things like additions or KZG commitments are done share-wise using PSS for efficiency. 4. Complex checks. For nonlinear parts, they use the specialized protocols. The product tree approach for PROCheck and the public input-based permutation check, likely relying on collaborative sum check protocols underneath. 5. Aggregation. All the intermediate results and partial proofs computed collaboratively via MPC are combined to produce the single final proof, 6 verification. This final proof is sent to the verifier. The verifier runs the standard verify algorithm from the original zk-SNARK scheme using the public statement and the CRS. They don't need to do anything different.
So from the outside looking in, the verifier just gets a normal snark proof. They have no idea about the complex, distributed, privacy-preserving computation that happened behind the scenes. That seamlessness seems like a huge win. And the practical impact you mentioned, distributed workload, less communication, faster speeds, that really opens things up.
Absolutely. The impact is significant. You get a system where the proving time and memory needed per server can actually decrease as you add more servers, scaling like 1n. Communication costs become much more manageable, sometimes even sublinear in the data size for certain types of circuits. And the concrete speedups, like that 30x example, show us not just theoretical. This makes it practical to apply zk-SNARKs to much larger problems or in settings where data is inherently distributed and can't be centralized, like secure audits or delegated computation.
So if you're dealing with really big computations or situations where the data has to stay separate, this collaborative approach, especially with these optimized MPC-friendly building blocks, seems like the most promising path forward.
For many large-scale or decentralized applications, yes, I think it represents a major step forward in practicality and scalability compared to trying to force everything onto a single prover or using generic MPC.
That was quite a journey through some pretty complex cryptography. We've really seen how collaborative zk-SNARKs build on the original ideas but adapt them very cleverly to allow groups to prove things together without sacrificing privacy. It's amazing how these tools can be engineered for such challenging real-world needs.
It really is. It's a great example of how smart cryptographic design, focusing on the algebraic structure and designing protocols specifically for MPC, can lift powerful single-party tools into this whole new realm of secure, scalable, multi-party collaboration. It definitely changes how we can think about trust and verification in decentralized systems.
So, wrapping up, what does this all mean for you, the listener? Imagine a future where these complex, siloed data problems we see everywhere, think medical research, financial systems, supply chains, imagine they can be unlocked. Data can be aggregated, analyzed, and verified across organizations, all without compromising a single piece of individual private information. What kinds of innovation, what level of trust, what sort of collective intelligence could that enable when we can genuinely compute on secrets without ever needing to reveal them? That's definitely something to ponder, and it's a future that collaborative zk-SNARKs are helping to build.